Our next speaker is Sami, Assaf. You're going to talk about a Pieri rule for key polynomials.
Thanks very much. Thanks to the organizers for keeping us all at this conference, wherever we are. I'm going to talk about joint work with my graduate student, Danjoseph Quijada. And yeah, so here's the plan. I'll start by talking about polynomials. I'll motivate everything from analogy with Schur polynomials, with which hopefully everyone here is familiar, but I'll be talking mostly about key polynomials, which is a non-symmetric generalization. And our main results I'll talk about in the second half of my talk, which is a combinatorial formula for Pieri rule for those. But to begin, let's go into the combinatorics, and we'll start with something that's very familiar that I'm not going to talk much about beyond the first slide, but just to kind of ground the combinatorics here. We can think about integer partitions. We can draw the Young diagram. Contrary to my normal convention, I'm using English notation, but hopefully you'll see why I need to do this for this talk. Here's the partition 54410. I can think about tableau, where I put numbers in the boxes. And the row condition is that numbers weakly increase. The column condition is that they're going to streakly decrease. And then I can fill out my entire tableau in this way. Of course, I want to try to write down all of the tableau I can for a given shape. So if I take the shape 2, 1, I need to tell you what my biggest number is, otherwise this will go on forever. So if I say my biggest number I can use is 3, then I can write down these 8 semi-standard Young tableau of shape 2, 1. Okay. And now from this, I'm going to take a generating function. So to take a generating function, I just need to tell you how to associate a monomial to every object. So here's my example. The weight function for tableau is I can change every box with a 3 to the variable x3, and then I multiply all my boxes together. So the weight of the example that I have at the top is given there. So we can see that x1 squared because they're 2 1s. And then for the Schur polynomial, I do this example in the middle, and I write down the monomials for all of the 8 tableau I get, and I get this symmetric polynomial. You can have multiplicity for the weight spaces, so that can come up there, not multiplicity-free. That's going to be an important topic. But Schur polynomials are a basis for symmetric functions. As we all know, they might be your favorite basis. That would certainly be a reasonable choice. And there's lots of really nice geometry and representation theory underlying them. So that's sort of the objects that we're going to start with, and now we're going to completely abandon that. And now what I'm going to talk about are key polynomials. I'm going to use, there are many, many, many different combinatorial models for these. I'm going to use the one developed by Axel Konert, who was a student of Lescaut. And we begin, instead of with the partition, we have a weak composition. So non-negative integers in some fixed order, but it doesn't matter what the order is. So 4, 1, 5, 0, 4. And I can draw this. I'm using Cartesian coordinates. So 4 bubbles in the bottom row, 1 in the second row, and so on up. And Konert's model says, begin with this diagram. Now, instead of filling the bubbles with numbers, we're just going to move the bubbles. So he says, okay, you can pick any row you like. Here I picked row 5. Take the bubble at the end of the row and push it down. So this is a Konert diagram for 4, 1, 5, 0, 4. But I can keep doing this. I can iterate it. So I could take that yellow bubble and I can push it down again. And Konert says, well, if there's a bubble in your way, that's fine. Just jump over it. Okay, so I've jumped over it. Now this is another Konert diagram. And I could take this bubble and I could push it down. I could take this bubble and push it down. Now I can't take this bubble. The bubble that's in, I'm not sure what color that is. It sort of looks reddish to me. So we take that reddish bubble. We can't push it down as a Konert move. That's not allowed because Konert moves say you have to take the bubble at the end of a row. However, if I did push it down, you might notice that the diagram I get is actually a Konert diagram for the shape with which I began. Because in row 3, right, I could push all 3 of those bubbles at the end of row 3 down. And then the bubbles in row 5, I could push the 2 rightmost bubbles down. And then I could get this diagram. So this diagram, even though the way I got it was illegal, this diagram is a valid Konert diagram for the shape with which I began. Okay, so this is Konert's model. It's an easy model to implement. And of course, we could try to generate all of the diagrams given an initial diagram. So let me take the diagram 0, 2, 1. It's a perfectly happy diagram. So I can start doing conart moves to it. So the 2 bubbles I could begin with. And so pushing down the one in row 2 or the one in row 3 gives me these 2 possible conart diagrams. And now on these bubble diagrams, I could push down again with Conart's rule, and I get these 5 diagrams, and that's it. There's nothing else that I can get. I will point out that this diagram on the right with that red cell, that red bubble at the bottom, is not a Conart diagram, because there's no way that red bubble could have gotten down there by a Conart move, by any sequence of Conart moves. Okay, so you can't just get anything. It's a restrictive condition. So these are the 5 bubble diagrams that I get, the Conart diagrams. And now I want to turn it into a polynomial. To turn it into a polynomial, once again, I'm just going to tell you how you get a weight associated, a monomial associated to every diagram. So here's the rule. There are no numbers, so that's clearly not how we'll do it. It's now based on what row that you're in. So if you look at the example on the top, x3 shows up with multiplicity 3 because there are 3 bubbles in row 3. There are 4 bubbles in row 1, so I get x1 to the 4th. So in this way, I can associate a monomial to every diagram. And if I take the generating polynomial for some fixed initial diagram, then I can get a polynomial. This is what I'll call a key polynomial. It's a theorem of Conart's that this is a key polynomial, and the definition of a key polynomial will come on the next slide. But I like the theorem better. So one thing to point out is this is not symmetric. I'm not doing symmetric polynomials anymore. Okay. For example, you don't see x1, x3 squared anywhere in this example. Okay. It's definitely not symmetric, but it could have been, and sometimes it is. But key polynomials are in fact a basis for all polynomials. They're a basis for the full polynomial ring. Okay. There are a lot more of them than there are Schur polynomials. They're linearly independent. You can see that with an easy triangularity argument. Okay, so I want this to be a somewhat familiar concept to you. So since you might be seeing this for the first time, let me just make an equivalence between key polynomials and Schur polynomials in a certain case. And so the theorem is that if you take a weakly increasing sequence, so that's a partition but sort of written reverse from my normal convention, you get a Schur polynomial, okay? And the number of variables is very specific. It's the length of your composition. So let's relate, therefore, the combinatorics of Conart diagrams with tableau, so that you can kind of maybe draw some analogies and understand these diagrams from your understanding of tableau. So Dominic Searles and I looked at this, and we defined the following very simple map. Okay, this is something that your 6-year-old should be able to do. So you start with a diagram. Here's a Conart diagram on the left. This was the diagram we played with on the first or the second slide for 41504. Label it, label all the bubbles. Okay, now you're doing it sort of reverse of what you might think. So from the bottom, you start labeling with N, and then you go up, and the top row N, gets labeled 1. There's some kind of reversing happening there. And now you fill your bubbles with helium. Don't let them change order, but they float to the top. Now we have a partition shape, and now you make your bubbles square. That's it. It's a very simple map. Okay. And what Dominic Searles and I proved is that this is, well, it's obviously weight reversing, right? Our notion of weights in Tableau was the numbers in the boxes, and the weights for bubbles is what row you're in, and this n minus I plus 1 reverses my weight. But this is an injective map. It's not obvious that what you get is a tableau, but it's in fact a theorem. For example, the 5 diagrams, the 5 Conart diagrams that we had before, map to these 5 semi-standard Young tableau that we saw. And in fact, what we proved is we have a bijection with tableau if and only if we're in this case of weakly increasing. And therefore, since Schur polynomials are symmetric, that means that generating polynomial has to be a Schur polynomial. Otherwise, it would have reversed everything, but by symmetry, that's fine that we reversed everything. I will say, if you don't want to reverse everything, and sometimes it's better not to have a weight reversing map, you can compose with the Schutz-Berger involution that sort of, and Schilling will like this, it flips the crystal. So if we compose with the Schutz-Berger involution, then we get a weight preserving map that respects a lot of the structure. Okay. And then One more thing to point out about corner diagrams is that this diagram on the left, I said, well, it's a corner diagram for 41504. That's true, but it's also a corner diagram for lots of other things. For example, 01445. If I look at that picture of the tableau there with the square boxes, that gives me a recipe for how to get that diagram back just by starting with the 5s and pushing them from right to left down to row 5. Then the 4s from right to left down to row 4, and so on. So that gives me a recipe following Conrad's model to get that same diagram. So if I give you a diagram and I tell you it's a Conrad diagram for something, you can't tell me what the something was that I was thinking of. Okay, it could be lots of different things. That's both a benefit and a drawback, and we'll see how that plays out. Okay. So where do these come from? So hopefully you see that the key polynomials generalize Schur polynomials, but they come from the same contexts in which we have Schur polynomials. So if I take irreducible representation for GLN, okay, it's going to be indexed by a partition, and I can decompose it into weight spaces. And whenever the weight happens to rearrange the partition, the dominant weight, then it's going to be one-dimensional, and a symmetric group acts permuting those. So one thing that de Mazur considered is, okay, what if I take one of these extremal vectors? So an extremal vector is just a vector with a weight that rearranges the highest weight. And now I act with upper triangular matrices. Okay, if I do that, I get some subset of my irreducible module. And that's what we'll call a de Mazur module. So just to make that a little concrete, here I've drawn the combinatorial skeleton of a module. This is the 8-dimensional irreducible representation indexed by 210 for GL3. Okay, each tableau, semi-standard Young tableau, indexes a basis element for this module. And they sort of have this basic structure here, which might be familiar. And now when I take a de Mazur module, I take this irreducible and I also pick an element of the vowel group. So I pick a permutation. So the simplest one I could pick is the identity. So if I pick the identity permutation, then what am I doing? I say start at that highest weight vector, okay, and go up by acting with upper triangular matrices. Well, the definition of a highest weight vector is there is no up. So I get a single one-dimensional submodule. Now, what if I lengthen my permutation and I do the permutation 1, 3, 2? Now I'm going to start at the extremal weight vector with weight 2, 0, 1, and I go up in the sense of acting with upper triangular matrices. So now I'm going to get a 2-dimensional subspace that includes this extremal vector and the highest weight, and that's it. Lengthen it again, 3, 1, 2. Now I'm starting with a weight 0, 2, 1, and when I act with upper triangular matrices, I get a 5-dimensional module. You might recognize these are the 5 tableaux that are the image of those Conrad diagrams. That's not a coincidence. That's actually a definition. And then by the time I act with the long element, I have the entire irreducible. So de Mazur modules interpolate between my highest weight vector and my full highest weight module. Okay, and they do it in a way that filters the module based on Bruhat order. So going up in Bruhat order is giving me a bigger module, a bigger submodule. So the definition is a de Mazur character is the character of this module, and de Mazur characters in type A, so when I'm talking about GLN, are key polynomials. Key polynomials, as I said, are indexed by weak compositions, and here I'm telling you to keep track of a highest weight and an element of the vowel group, but keep in mind when we take a permutation and we act on a partition, we can just think of that as the composition that we get, and that's a dictionary between them. So in terms of these characters, what the example that I have is the key polynomials interpolate between the single leading monomial and the full Schur polynomial, and they give me pieces in between. Okay, so again, key polynomials are polynomials. They're not always symmetric. They're a basis for the full polynomial ring. With Schur polynomials, they're a basis for symmetric polynomials, and when we multiply them, that corresponds to tensor representations, so that means something. Now, what we're gonna wanna do, is say, okay, well, can we multiply key polynomials, right? That's a natural question, and the answer is, of course, because they're a basis, but what you get is a mess. because this idea of taking upper triangular matrices and acting doesn't respect the tensor structure. So it's not that we're going to get another de Major module when we tensor. So somehow, even though this is motivated from the representation theory, the questions we ask in representation theory don't quite manifest as nicely in this more general setting. So you might wonder, why do I still want to multiply? Especially being a combinatorialist, negative signs generally turn me off. But there's a lot of structure here anyway. And sometimes the answer is positive. And when it is positive, sometimes I really care about the answer. So let me give you the second half of my motivation, which comes from Schubert calculus. We're going to hear a lot about Schubert calculus tomorrow morning from John Treshan and Alex Young. And I'm going to leave it to them to define Schubert polynomials. Maybe Alex will. But let's just say Schubert polynomials are polynomial representatives of Schubert classes for the flag manifold in type A. Their structure constants for Schubert polynomials give us the structure constants in cohomology. And so they're positive. They count something geometric that we would really love to have a formula for. So Schubert polynomials are super interesting. If you take they're indexed by permutations. And if you take the permutation to have a single descent, that's what we'll call a Grassmannian permutation. It's called a Grassmannian because the variety we're looking at is a Grassmannian variety, and the Schubert polynomial that we're looking at is a Schur polynomial. Schubert polynomials are another way to generalize Schur polynomials to the full polynomial ring, because Schuberts in general are not symmetric. Now there's a different condition instead of Grassmannian we could take. It's called vexillary. You can see if you look carefully at this pattern avoidance condition that a Grassmannian permutation is always going to be vexillary. It's a special case. But vexillary is a more general concept. Of course, not every permutation is vexillary. But if your permutation is vexillary, then your Schubert polynomial is a key polynomial. They coincide in this case. So it's not the case that every key is a Schubert or that every Schubert is a key, but they do overlap in this very important vexillary case. More generally, Lascaux and Schutz and Berger sketched a proof, perhaps is fair to say, that Schubert polynomials are positive sums of key polynomials. Reiner and Shimizono did a really beautiful paper analyzing all the combinatorics of key polynomials. I highly recommend that paper. And they gave a rigorous proof to this result, which is the Schubert is a sum of keys. Okay, so what that vexillary condition tells us is exactly when the sum has a single term in it, but it's always positive. So positive, what does that mean? Well, remember that Schubert polynomials, we multiply them and put them back in Schuberts and it's positive. We know that from geometry. We do not have a combinatorial understanding of that in general, but we know it from the geometry. So let's combine that with this theorem of Lascaux, Schutz and Berger, Reiner and Shimizono. If we multiply two vexillary Schubert polynomials, it's a positive sum of Schuberts, which is a positive sum of keys. So in this case, vexillary key polynomials, if I can abuse that notation for a moment, actually gives me a positive expansion. So even though key polynomials in general multiply and give me negative signs, sometimes they don't. And in this particular case, not only do they not give me negative signs, but they give me some really interesting numbers that I would really like to be able to compute. So that's the motivation portion of my talk. And I see the chat's flashing, but I can't find the chat here. So I'll trust Angela to chime in if I should stop for questions.
You're good, Sami.
All right, cool. All right, so this is why I should care. Multiply key polynomials, I expect it to be a mess, but sometimes it's nice, so I still want to try to understand it. And now we'll go into the second half of my talk, which is how do we understand it? So first, right, let me motivate it with reminding you about how to multiply Schur polynomials, because everything's built on analogy. So we can multiply Schur polynomials. We get positivity from the representation theory or from the geometry, actually from both. So it's definitely positive. Pieri, long before these connections, gave us the formula. So let me do it in a single box. So here's the equation. Equations are great. Let me draw the picture. Those are so much better. So here's my favorite partition for today, 5, 4, 4, 1, okay? Drawn in English notation. I'm multiplying by a box. Pieri says, just add a box. Okay, all possible ways that I can add a box. That's my expansion. It's multiplicity-free. And it's this really nice concrete thing. Again, your 6-year-old can compute this from this rule. It's very simple. Okay, but Pieri actually told us how to do it for a single row, and that's not much harder. So what do? Well, we're going to add, say we want to multiply by S2 now. I've changed my favorite partition to 3, 2, 2, and I'm going to multiply by S2. So I'm going to add 2 boxes, and the only caveat is that I mustn't add them in the same column. Okay, so I could add 2 boxes here, or here and here, or here and here, or there, or there. 5 terms, multiplicity-free, super easy to do. Just add boxes in a horizontal strip. So you're not allowed to add 2 in the same column. And this is a beautiful statement. It's absolutely gorgeous. And the proof is equally gorgeous. So you can prove this using RSK. So you can insert a number into a tableau. That number you're inserting corresponds to a tableau with 1 box. And when you insert it, you're exactly going to get a box with tableau shape with one more box added, and it's reversible. And this is exactly a bijection between these sets of semi-standard young tableau. And then down here for the 2, if you're adding 2 boxes, there's a row bumping lemma. So a row bumping lemma just says that when I add in a weakly increasing order, I get a horizontal strip. So again, it's a really, really beautiful proof, and it works. It works in general. So it's a beautiful result with a beautiful proof. Again, we're not expecting it to be that nice in the key polynomial case, but it certainly gives us hope that if it's this nice, a few things can break and it'll still not be bad, hopefully. All right, so what do? Well, remember, if we think about a Schur polynomial times a box, what do? We add 1 to a part of lambda. Now, you can't just do it willy-nilly to any part, but that's the idea. You add 1 to a part of lambda. So maybe when we multiply a key polynomial by a single box key polynomial, and now for key polynomials, I care where that bubble is, right? It matters what row. So let's say in row K, then I'm going to add a bubble to some row of A that I start with, and there are going to be some conditions. This is what I'm expecting. So we can compute an example. So here's an example for my favorite composition, 41504. I'm adding a bubble in row 3. That's what K001 means. It means there's a bubble in row 3, okay? And what I get is, well, it's kind of a mess when you just look at it. Certainly that negative sign's a bit of a downer, but let's try to make sense of it anyway. So here I've drawn my bubble diagram for the weak composition 41504, and I've drawn a horizontal line at row 3, because Conrad's model tells us that when we're putting a bubble in row 3, that bubble can't go up. It has to only go down. So that's why I put that line there. So I'm going to add a bubble, and I don't want to do it above row 3. And look, in my first term, if I think about the first term in that expansion, I can think of that as adding a bubble in the second column, second row. And that's exactly what I've done. I've taken the weak composition and I've added a bubble. That is super nice. That's just like Pieri's formula. Okay, so can we keep doing it? Well, the second one, absolutely. I've added a bubble in column 5, and that's in row 1, and I've just added a part, and that's low enough that I'm allowed to add it there. It's below 3 in this case. That's fantastic. And so the next one, well, now it sort of breaks down a little bit, but if you draw the picture, you see the structure. And the structure is exactly given to us by Conrad's model. So remember, bubbles go down. So if we take those bubbles in row 5 and drop them down to row 2, then all of a sudden we can add another bubble at the end of row 2 over there in column 5. That's exactly what this term is telling us. 45501 is we've dropped some bubbles down and added. And that's a very Conard style thing to do. Dropping bubbles is totally allowed. And in fact, it's sort of taking advantage of something called the left swap order that Dominic Searles and I studied when we were studying Conard's modeling and key polynomials earlier. And my grad student, Danjoseph, noticed this connection. So we can write everything in terms of this sort of go down in Bruja order thing and add a bubble. Let's skip the negative term for a second and jump to the end and say, aha, now I've added something in row 3, column 6. So all of my positive terms I can make sense of, and I can draw a picture that really suits them. That's pretty exciting. What about the negative sign? Well, that's got a negative sign. but is there some way to think of it anyway in terms of these diagrams and in terms of sets? And this was one great observation. So the reason that Conant's model is the right model to use in this is exactly because it's ambiguous. If I take the set of Conant diagrams for 51504 and the set of Conant diagrams for 45501, they have a non-trivial intersection, and their intersection is exactly that negative term. So this was the great observation, and it's due to my grad student, Danjoseph Quijada. He noticed this, that like that's exactly what's happening on these negative terms. It's the intersection of these sets. So negative signs are coming up in the nicest possible way. There's no sign reversing involution. There's nothing hard that I have to do here. And our theorem is that, well, sorry, for this example, each of these groups of terms, now let's group the negative term together, can be thought of as something positive. It can be thought of as a union. And my signs just come up from inclusion, exclusion, which is a very combinatorial thing and something that shouldn't make us so nervous. And in fact, what DJ and I have is a bijection from sets. And there's nothing negative in our bijection. There's no involution that reverses anything. But when you take the generating polynomial of it, you have to remember to do inclusion, exclusion, and therein lies your signs. Okay, so I want to say a word about the proof of this. Actually, probably several words, but I really like the proof of this. So I want to give you at least a sense of how it goes, because I really like this statement. And the proof's not so bad either. So going back to earlier work that I did with Dominic Searles, we gave a characterization of, if I just hand you a diagram, can you tell if it is a Conant diagram for something? Never mind for what, but for something. And yes, it turns out, here's the characterization, but let me tell it to you graphically. In column 2, can you match every bubble in column 2 to a bubble in column 1 that's weakly above it? Yes. Okay. What about from column 3? Can you match everything to column 2? Yes. And 4? Yes. 5? Yes. Okay, then this is a Conant diagram. That's exactly what it says. It's about matching from columns to the left and go weakly up. And there's a greedy way you can do this, but never mind that. Let me tell you about this process called rectification, and then I'll justify why I call it rectification. So start with the Conant diagram. That's my favorite Conant diagram that I've been using several times in this talk. And then add a bubble to it, okay? And in your head, if you're thinking RSK, that's not a bad thing to think, and more on that in a second. So let's add a bubble. Now, first test, do you have a Conant diagram? In this case, no, because that bubble doesn't match to anything weakly above it in the next column. So it's not a Conant diagram. Theorem, if it's not a Conant diagram, there's a unique bubble that makes it fail. That's specific to I'm adding a bubble to a Conant diagram, but it's true in that case. Okay, there's a unique bubble that doesn't match. Okay, fine, move that bubble left. Iterate, try to match it. Does it match? No, that bubble still doesn't match to anything. Fine, move the bubble left. Okay, try to match it. Does it match? Yes, the bubble matches, but now this bubble doesn't. That's a bump. Okay, fine, move the bubble that doesn't match to the left. Okay, does everything match? Well, that bubble matches, but now this bubble doesn't. Fine, move it to the left. Okay, great. Does everything match? Yes, that's the end result of rectification. This is RSK. This is RSK translated through to Conant's model. It's more general than RSK because it handles a much more general context of things. I could just throw bubbles around and still do this, and it makes some kind of sense. Okay, but if I were to start with the skew diagram, then it would correspond to rectification in Juratican's sense. And if I insert something, it corresponds to RSK. So this is a nice bubble way to think of it. And in fact, whenever we're inserting our bubbles high enough, RSK is our bijection, okay? Thought of in this way. And unfortunately, it doesn't work in general because everything gets a little more complicated. And what we have to do is sort of rectify a piece of a diagram instead of the whole thing, and we sort of do it backward as well. So there is a complication, and our proof is 65 pages long, so it's fair to say it's fairly complicated, but it still works, and this is still the core idea behind it. So there is some nice combinatorics in here. And then finally, I guess I have 5 minutes, so let me tell you, if you notice here that red bubble moved down and to the left, right? That's the row bumping lemma that we need to get the Pieri rule. So I told you how to add a box, and let me show you how to add multiple bubbles. again, there are two conditions. So the condition one is don't put your bubbles too high. So we can drop bubbles down and add a bubble, never add a bubble too high, right? And the second condition is don't add bubbles in the same column. Okay, so let me do an example. 2032. Let's add two bubbles. This is the same example I did symmetrically before, but now it's not symmetric anymore. It's a key polynomial thing. I could add these two bubbles, and it matters what columns I'm adding in. I could add these two bubbles. So if I add bubbles in columns 1 and 3, there are two ways to do it. That's going to give me an inclusion-exclusion term. That's going to give me a negative sign. One way to add in columns 1 and 4, two ways to add in columns 3 and 4. So I'm going to pick up another negative sign. And then one way to add in these two columns, and that's it. So now we have a perfect understanding of the Pieri case. We know where all the terms come from, we know why we get negative signs, and we know when we get negative signs. And it's important that we know when. Now that we know where they come from, we can avoid them. So let me give you a few examples where we have positive expansions. So many more examples of adding bubbles to come. So if I take the composition, I guess I'm now doing 1, 4, 0, 3, and I want to add two bubbles, and I do it at the top. So in row 4, in this case, then this is going to be the most directly analogous to the classic Pieri case. I just go through and add my bubbles. Nobody ever drops. No bubbles drop down. So the dropping bubbles of my diagram rule only happens if they're above row K and they drop below row K. So there's nothing to drop here. And in fact, this is a special case of a more general result by Hagelin, Luoto, Mason, and Van Willigenberg, where they multiply a key polynomial by a Schur polynomial as long as the Schur polynomial has enough variables, okay? So if the Schur polynomial has n variables and your key polynomial is indexed by a composition of length n, they can do it for general lambda. And this corresponds to exactly what they've done. But what their theorem doesn't touch on is what happens when I insert it somewhere else. So now think about the other extreme case. Let's insert into row 1, right? I'm multiplying by x1 to the m. It's something you can do in the key polynomial. You still want to understand it. Now, there's not ever two ways to do something. I can either add the cells or I can't. So there are cases where I can't. So I can't add in column 1, for example. The first time I can add is in columns 2 and 3, but I still get a positive expansion. I'm sometimes dropping bubbles down, but my extension is still positive. And then if you want to understand our proof, essentially our proof interpolates between the case at the top that's handled by this rectification process and the case at the bottom, which has actually a simpler insertion rule, but somehow the interpolating between them gets nice and complicated. And then I will end with one more example. So my final example, okay, that maybe looks daunting, but the point is that we take a vexillary key polynomial, a vexillary Schubert polynomial, and we multiply it, and we're going to get a Pieri rule that's manifestly positive. Our formula is cancellation free. We get a precise, exact formula. There's no cancellation that happens. So there are no negative terms that happen here because we knew from the geometry that we had to get a positive expansion. So I can't use the same composition I was using on the previous slide because that one's not vexillary. This is vexillary, 0, 1, 4, 3. I'm inserting at row 3 because I have 3 variables for my Schur. And it's the vexillary condition as described by McDonald on compositions. So that's in McDonald's notes from 1991. It exactly says that we're never going to get two ways to do it. It's sort of, our rule really loves McDonald's characterization of vexillary, which is kind of nice. So now, okay, we can add in these columns, add in these columns, and we go through and we add in all possible ways, and there's our expansion. In this particular example, it turns out that each one of these key polynomials is also vexillary. I've just multiplied Schubert polynomials for this example. In general, we're getting a key polynomial expansion. If we want to get back up to Schubert's, I don't see a way to do that without some kind of sign reversing involution. But at least in the Pieri case, you can see the Pieri rule for vexillary Schubert polynomials coming out of this rule. It's sort of very suggestive of that. So there's hope that by studying the key polynomials and studying their products, we can get some understanding of the product of vexillary Schubert polynomials and maybe get something more beyond that. So I will leave you with these references. So we have a paper that appeared in FIPSAC in 2018 where we conjectured our rule. We have a preprint out on the archive where we prove our Pieri rule, and we say it in a slightly nicer way. And then I'd like to advertise as well my paper with Dominic Searles, where we studied, that lays a lot of the combinatorial foundation, where we studied the Coinert tableau. And if you want to know more about rectification, I study that in a more recent preprint. So thank you very much.
Okay, so let us thank Sami for a beautiful talk. Thank you. I'm going to go over to Angela.
I stop my share. Okay.
Great. Thanks, Sami. I think Yuval had a question in the chat just before this ended. Do you want to go ahead and ask it? Okay, I will go ahead and repeat it. The question was, can you characterize when the expansion is positive? And then the question was, is that if and only if it's vexillary?
That's a great question. So it's not if and only if it's vexillary. So McDonald characterizes the vexillary condition on compositions, and there are two characterizations. And one is about, okay, if you have a long row above a short row and the other one's a short row above a long row, we only need one of those to guarantee positivity, not the other one. So it is more general. And we have written down, like, it comes down to, if you can never add in the same set of columns in two different ways, it's positive, and that's if and only if. But in terms of a specific condition on compositions, we know that the one McDonald condition, which he calls C2, is enough to guarantee it, but I don't think it's if and only if.
Okay, we have several more in the chat. Jianping Pan, do you want to go ahead and take the next question? Go ahead.
Hi, just want to ask if this result extends to the stable version for the Schubert polynomials.
Yeah, well, it's sort of unfair to say it extends to it. Maybe it's fair to say this is inspired by it. In the stable case, right, what we get is a Stanley symmetric function, and Edelman-Green insertion is like the generalization of RSK, and that is what's going on here in the stable version. So sort of this was inspired by looking at that case. So it sort of yeah, the direction's wrong. Yeah, I could totally understand it using this, but that's sort of a bit circular.
Okay, thank you.
But yes, it's definitely connected and related.
Vic, go ahead.
Yeah, thanks, Angela. Nice talk, Sami. I want to ask, so those inclusion-exclusion sums, I think they have this model as just like the de Mazur character is, you take some space of global sections of some line model, you restrict to a Schubert variety. I think they're when you restrict to a union of Schubert varieties, or there's these sums of de Mazur atoms over an order ideal in Bruja order. So is there any kind of de Mazur crystal-like model, the way that you have for de Mazur characters, that could help improving these kinds of results?
That's such a great question. So one of my other grad students, Nicole Gonzalez, who's now at UCLA, she's actually looking at how to understand the tensor structure of de Mazur crystals. So like when we tensor de Mazur crystals, it's not a de Mazur crystal, but there should be some way that it comes out as like an inclusion-exclusion of crystals. And she's kind of looking at that. From the geometric side, though, I'm not so sure. But from the crystal side, it's not totally clear how that should work. But we do, like Anne Schillen and I have a de Mazur crystal model on an equivalent combinatorics for the key polynomials that generalizes her work with Jennifer Morris on Stanley symmetric crystals. So we know what the crystal looks like very combinatorially and concretely. But in terms of multiplying them, that's still open.
Sarah, and then I'll try to switch over to the hands.
Wonderful talk, Sami. Thanks so much. I had a question too, which is actually kind of related, but maybe slightly different point of view than Vic's. So in terms of your inclusion, exclusion, I was wondering if you could reinterpret that like the Reiner-Shimizuno expansion of a Schur polynomial into keys. Like you care about how the reduced words break up according to their Edmund-Green tableau. And can you view the inclusion, exclusion on that level?
Right, that's a great question. So I'll say that if you start with vexillary Schuberts, then yes, you can do that and you can make sense of it. But if you just start with a generic key polynomial that's not necessarily a Schubert, then yes, but it's a really awful mess. So the way I was originally trying to solve this problem was using a similar method, and it was a mess and it's just awful. And until DJ told me that I was doing it all wrong and that I really needed to use Conrad's model, it was hopeless. So it's just an unholy mess, because you need the idea of Conrad's model that allows you to see that it lives in multiple sets at once. And if you start playing with words, then you can't see that. So somehow this nested structure only really comes up in this model.
Okay, great.
If that makes any sense. So when you start using the words and you start using that word characterization, you lose the sense of how they're related.
All right. Well, thank you. Actually, that's great. I guess we'll call that open problem. More work to be done. So just because I'm watching the time, I think let's start thinking about moving to breakout sessions. But before we do, I have a couple of announcements. And I'd like to thank both speakers one more time for such a great session again. So thank you very much. And feel free to post in the chat if you have thanks or applause, so that we have sort of a permanent record of that to share with the speakers.